So in our first video about the EM algorithm, one of the contextual examples that we looked at was linear regression with missing inputs. So we're going to revisit this now. So let's say we have some two-dimensional inputs. So we've got something called x, and we have let's say we've got an x1 first component, x1 second component, x2 first component, x2 second component, down to xn first and second components. And then we've observed some outputs, so this capital Y is going to be n corresponding outputs that we've observed. And we're going to propose a model that gets us from each x to each y. So in this case, we're going to do linear regression, linear in the parameters and the inputs. So I'm going to suggest a model which says, okay, we think that, let's say f of xn, so let's say vector xn, that's one of these vectors. And we're just going to say, okay, it's equal to some parameters, let's say parameter 1 and parameter 2, so that's a vector, multiplied by first component of xn and then the first component of the second component of xn. And we're also going to account for the fact that these y's could have been observed as part of some kind of noisy process. So it could have been measured, they could have been measured by a sensor that's corrupted with measurement noise. So we'll say that each y is equal to the output of our model. Again, sorry, x is a vector, plus some kind of noise. And for now, we're going to assume that that noise is Gaussian. So it's being drawn from a normal distribution, let's say with zero mean and variance sigma squared. So this is the model that we're going to use, and then this is what's often called a noise model. And it says that there might be some uncertainty in our observations of y. And then we say, well, what happens if some of these inputs are missing? Okay, so let's say that, you know, the sensor broke or something, and so we don't have, let's say, this input, and perhaps some others are missing too. So just as an example, we've got some Python code here where we've got some 2D inputs, which are shown here. So these are just like the x's written here. And there's some missing, okay? So we have not a number there and not a number there. And then we have some noisy observations, which are written as y here. And then we're going to run some code that tries to find out what these parameters are, θ1 and θ2, and also estimates what these missing values are. Okay, so here are our parameter estimates converging, so that's θ1 and θ2. And then here we have probabilistic estimates of what our two missing data points should be, as well as on here I've marked what the actual true value of these missing data points are. And this is all done with the EM algorithm. So we'll look at how that works now. So the notation here can get quite complicated because you can have, you can imagine you can have multiple x vectors that contain missing components, and you might have an x vector that's containing, say in this case, it might have more than one missing component. So what we're going to do is we're going to keep things simple, just so that the notation is kind of a bit more bearable. And then we'll say that once you've been through this kind of tutorial, it's easy to take this method and generalize it more. So let's just say that we only have a single missing component. So let's say that we only have only xm has a missing component. So what we're going to do is just correct what we've said about our model. We're going to say that this is true. This fn is equal to these theta1 and theta2 multiplied by xn, the vector xn, but only for the case where n is not equal to m. Otherwise, what we have is this is really equal to theta1 and theta2 times by, and let's say we just have an xm, and also we have a single missing component, and I'll just call that zm. And to keep the notation simple, rather than putting x in brackets here, we'll just call this fn and fm. Okay, so now this is a case where we can apply the EM algorithm because we want to estimate these parameters, theta1 and theta2, and also we want to estimate this missing data point, zm in this case. Right, so it's slightly different notation to earlier, that the x's mean something different, but that's okay, it's still the same general approach. So the first thing we need to do is look at our E step, which as we've seen before, involves finding the expectation with respect to the posterior distribution over our latent variables. We just have one in this case, which is Zm. So posterior of Zm given, and basically all the other stuff. So we've got x and y. So that's all the other data that we've got. And again, we say we've got our parameters fixed equal to our current best guess, and we're going to write that as theta I. And it's the expected value of the joint probability distribution of our data, logged. So in this case, it's log probability of, so we've got our observations, our latent variables, conditional on the inputs, that's just the known inputs, so it doesn't include Zm, and conditional on theta, where, as we've seen before, theta is not fixed equal to theta I. Okay, so just as before, we need to, let's say we're going to start by working out what this posterior distribution over Zm can be. And we're going to do that by writing Bayes' theorem. So we're going to say that the probability of Zm conditional on x, y, and theta I is proportional to probability of witnessing y conditional on Zm, x, and theta I. And then we had our prior, which is, we're just going to say probability of Zm. And we're going to say it's not conditional on x in this particular case. Okay, so our likelihood is essentially given by the noise model here. This is the product of capital N different PDFs, but only one of them contains Zm. And that's the only one that we're interested in. So we're going to ignore the others and we'll just say, well, this is proportional to the probability of witnessing Ym given Zm and Xm. still conditional on theta I, and then we have our prior, Zm. And this is up to us. We can choose what this is going to be. So what I'm going to do is deliberately choose something simple, just for this kind of example. Again, once you've been through all this, if you want to use a more complicated prior, then it's essentially the same maths. If you want to make this more general, so for now, I'm going to say, well, we've chosen that our prior over our missing data point, Zm, is Gaussian. And just to make it really easy, we'll say it has 0 mean and unit variance. And then this, so I'll use a different color. So that is given by our noise model, which is up here. So this thing is a normal distribution with ym as the argument. And then the mean is equal to the response of our model at the mth input, so that's here. So that is a theta 1 times xm plus theta 2 times Zm. And then the variance is the variance of the noise here, which is sigma squared. Okay. So what we have is that the posterior over Zm is a product of two normal distributions, and this is linear in terms of Zm. And we've done this deliberately. It's convenient because it means that we can combine these two distributions, and essentially you can rearrange it to find that the posterior over Zm is also a Gaussian. Okay, so we can go through that. So let's say this is, we won't spend too much time on it, but let's say this is equal to, again, this is all up to a constant of proportionality. So, okay, all right. It's proportional to, let's say, an exponential times minus a half. I'm going to write this thing called phi. So if you go through this, if you work through the maths, you can find that. So we'll change colour. Go down here. Phi is equal to. Okay, so coming from this stuff, we have a sigma to the minus 2. So this is our noise term, multiplied by ym minus the mean. So that's ym minus this stuff. Squared. And then from this, what we have is just a Zm squared divided by 2, because it's 0 mean and unit variance. And then we just do something called completing the square, where basically we collect together all the terms that are multiplied by Zm squared, all the terms that are multiplied by minus 2 Zm, and then we call everything else just a constant. So if you work through the maths, what you'll end up with, so we won't spend too much time on it here, but it's easy to show that you'll end up with a Zm squared multiplied by a sigma to the minus 2 times theta 2 squared plus 1, and then a minus 2z multiplied by, and this is a bit longer, so we end up with a sigma to the minus 2 theta 2 ym minus sigma to the minus 2 theta 1 theta 2 xm plus some constant, which I'll just call c, So the reason we write it out like this is now we can say, okay, let's just call this stuff A, and this stuff B. And it means we can write this all as A times Z minus B divided by A squared plus another constant. So that means if you substitute that into here, what it means is that our posterior over Z is going to be, so I'll bring it back. So it's going to be equal to a normal distribution, where obviously the argument is Zm. So I should say, I forgot to write, just to be careful, that is a Zm there, and that is a Zm, just to be clear. So it's a normal distribution, this posterior, the argument is Zm, and it's got mean B divided by A. Both of these depend on theta. They have thetas in them. So this is B with theta fixed equal to theta I divided by A with theta fixed equal to theta I. And then the variance is 1 over this. So we have we'll just write A theta I to the minus 1. Okay, so there we have it. Now we have our posterior over Zm. So that's what we'll be taking the expectation with respect to. So now we've been through all of that. I'll delete this and this. And let's say we put that here. So now we can simply write that our E step is to find the expected value of log P of Y and Z given X and theta with respect to this posterior, where the posterior is equal to this Gaussian distribution. Okay, so what is this distribution? Well, the probability of Y and Z given X and theta is equal to the probability of Y given Z and everything else multiplied by the probability of Z. That's our prior again. And then this we can expand. So what we're going to do is separate out the parts where we have missing inputs and where we don't. So this is equal to, let's say it's the product over all the n's that are not equal to m. So this is where we don't have missing inputs. And that will be a normal distribution. With yn as the argument, and then the mean is the response of the predictions of our models. That's still theta times by a vector xn, and then the noise is sigma squared. Noise variance is sigma squared, and then we include the part where we do have missing data. So that's normal distribution, and this time it's ym, where we've got this theta 1 times xm plus theta 2 times zm, and the variance is still sigma squared. So that is the likelihood, and then the prior is the same as before, so put that up here. So that's a normal distribution over Zm. It's zero mean and unit variance. So that means we know that the logarithm of this is going to be equal to, so we're going to take the logarithm of this first, of this green expression first. So that's a product. So when we take the logarithm, we'll end up with a summation. So it's a summation where n is not equal to m of the logarithm of this. And then I'll write it underneath. Let's say plus this thing, which includes our missing data point. And again, we've taken the logarithm and then plus log of this thing, which is the prior over Zm. Okay, now remember, once we've taken the expectation of this expression with respect to z, in the maximisation step, we then differentiate that with respect to theta. We differentiate this expression with respect to theta. So there's thetas in all these terms, but there's no thetas here. So this is going to disappear when we differentiate it. So for that reason, I'm just going to delete it. Delete our prior here. We'll just call that a constant. Okay. And then this will all be equal to, so again, only including the parts that are a function of theta. So we're going to have the summation of where n is not equal to m. And the log of this normal distribution here, so we're going to end up with a minus 1 over 2 sigma squared multiplied by yn minus the mean, theta transpose times xn squared. Then for this here, we're going to have a minus 1 over 2 sigma squared multiplied by now ym as the argument, minus the mean, which in this case is all this stuff. Squared. Plus our constant. Okay, so you can imagine that if we now expanded out this term here, what we're going to end up with is multiples of Zm and multiples of Zm squared. So this contains, let's just say, Zm and Zm squared. So this implies that when we take the expectation of this expression with respect to the posterior over Zm, what we're going to need is so this implies that we need to find the expected value, and it's the expected value again with respect to this posterior. Okay, we're going to have to find the expected Zm, and we're going to have to find the expected Zm squared. Okay, and we've already done that. So we know that the expected Zm is just equal to b divided by a. So b divided by a, that's fine. And to find Zm squared, all we need is the very well-known expression that the variance of Zm is equal to the expected value of Zm squared minus the expected value of Zm squared. We know that the variance of Zm is equal to a to the minus 1. We showed that earlier. And that's going to be equal to the expected value of Zm squared minus, and this final term is just the mean, so that is b over a squared. So from that we know that the expected value of Zm squared, just by rearranging this thing down here, is going to be equal to a to the minus 1 plus b over a squared. Okay. So now we've calculated all the expected values that we're going to need. So really we've completed our E step. So I'll remove the things we no longer need. So we'll remove all of this. And this is our log PDF. This is what we're going to differentiate with respect to theta in the M step. And we know that at some point we're going to need, in that expression, the expected value of Zm and the expected value of Zm squared. So we'll put those up here. So this all comes from there. So it's more convenient at this point to proceed with the M step next, and then just find out where these expected Zs and expected Z squareds fit into the final expression for the next best guess at the parameters. So in the next video we will look at the M step for this linear regression problem with missing data points.